Hi, I'm Fariba Choudhury. This is a walkthrough of AgriCarbon Lite, which is a prototype I built for my project for COMP482 Assignment 3 at Athabasca University. So AgriCarbon Lite is a greenhouse gas emissions tracker, and this was designed to allow small to medium prairie farmers to track greenhouse gas emissions that occur through different operations on their farms. So this video, I'll walk through the scope of the system, the tasks it supports, how I went from low fidelity sketches to a working Java prototype, the design choices I made, as well as a live tour of the 7 main screens. So I'm going to start with talking about the goal of something like this. So this model is to address the gap that producers in the Canadian prairies are increasingly asked to report greenhouse gas emissions for their operations. So this is something of interest to grain buyers, financial institutions that are running environmental research questionnaires, federal sustainability programs, policymakers, etc. So the science of farm level emissions accounting is largely settled. Uh, the this was built in inspiration from my personal work experience. I worked with the Hollows model. The Hollows model is a robust, grand scale emissions model that was developed by the Canadian federal government and the Department of Agriculture, and I did an internship there working on the Hollows model. And the Department of Agriculture Canada maintains the Hollows model, but it requires expertise to operate. So producers fall back on spreadsheets that are easy to use, but they produce numbers that have no resources to them on the actual platform. So that's one of like kind of the main thing that this prototype that I built in inspiration to something like Hollows, but the numbers with that are backed up by resources, that's something that I have kind of tried to incorporate more onto this platform. So therefore the gap is a usability gap in something like the Hollows model. AgriCarbon Lite is a producer-facing front end that uses the same IPCC and the same Hollows emissions factors, but hides the configuration complexity behind those defaults. The target user is a working farmer running up to 800 hectare mixed beef and grain operations, and they are comfortable with the smartphone, but they don't have to be a technology user. The main tasks, so this system supports 7 main tasks that I identified through task center design. Task 1, initial farm profile setup, so capturing the farm boundary, land use breakdown, and a livestock summary. Task 2, logging a fertilizer app immediately after a field pass, often from a phone and often done online. Task 3, updating year-end livestock figures. Task 4, exploring a what-if scenario like switching to no-till or reduced tillage or even reducing synthetic nitrogen, for example. Task 5, generating a year-end report for a grain buyer, which is very important, generating the report of the actual emissions and etc. Task 6, correcting a historical entry and reissuing that report with those corrections. Task 7, sharing read-only access with the farm advisor for review. And these 7 tasks together cover the full annual workflow of a producer who needs credible emissions data and accounting. So for assignment 1, I had produced 7 hand-drawn sketches, 1 per task, and these were deliberately rough sketches to allow room for criticism. I then ran a task-centered walkthrough, so for each task asking which sketches the user touches, what they need to know to take the next step, what they actually see, and what could possibly go wrong. The walkthrough surfaced some critical problems which I had to think about before even writing the code for this. So a missing fast path for in-the-moment logging, wake representation of offline status, no flow for the edit and republishing cases, and no sketches that covered advisor sharing. So these are the 4 critical issues that I realized that I needed to address before starting to write the code for this prototype. So 3 of those issues, they drove changes in the implementation of this final prototype, and then the 4th issue was deferred. So that's why it's important to kind of think more deeply about some critical gaps in a prototype before we actually start writing the code. So this working prototype is built in Java 21 with Swing. There are no third-party libraries. Everything is standard Java. Data is using Java serialization to a single file in the user's home directory, so that's enough for a working prototype. The calculator model is a pure Java class, and it could be swapped for a real Holos integration later without changing the UI, for example. This is the home dashboard. Headline total is at the top. So breakdown by sources is on the left. Recent activity is here, and these are quick actions. So these quick actions reorder by season. For example, in April, it will lead with fertilizer log, and in November, it will lead with update livestock. So click on farm setup, and the postal code derives the ecozone, so this is read only. The land use breakdown has a live sum check, so for example, if I change one of these values, it no longer adds up, so you can see the warning appears immediately. So I'll just change it back. Okay, the livestock. This design choice here is the live emissions feedback panel. So as I change the herd count to 100, the enteric methane figure updates in real time. So here, yes, so the enteric methane figure updates in real time. Every number on the screen is clickable to reveal the IPCC emissions factor. Every number on the screen is clickable to reveal the IPCC emissions factor and the source it came from. So the Fields tab. This is a pretty detailed layout. So field list is here on the left, detail form in the middle, fertilizer application at the bottom. The N per hectare total is computed live. So let's put 120, field saved. Okay, so as you can see, 120 of this urea product, so this is so one thing I want to flag is if you go here and you can add application, and then you can really just put in any numbers here. So I can put in 5,000, for example, and the system will never flag it. It will just save whatever data entries that the user puts in. This was done deliberately because we don't know what producers are doing on their farms and the details of their operation that goes on. So it's important to not have concrete ranges, and so producers can just input any data entry into the system, and then the system here, as it shows above regional average, it does still tell the user that, you know, this, hey, you might want to recheck this. It may not be right, but it won't stop the user from saving it as that, because again, we don't know what goes on, what specific farm operations the user has on their farm. So the next is the results. The next is the emissions results tab. So at the top, this is the annual total of CO2 emissions on this farm. There's this view as tab, which has the total, and then it has per hectare or per HA, per T product. So there's those options. There's a breakdown by source. So there's a breakdown by source here of there's a breakdown by source here, and then below that, as you can see, the bottom lists the emissions factor citation for every category. So as I had mentioned in my kind of introductory spiel, this is a no number without a source principle. So the bottom here lists the emissions factor citation for every category. So again, as I had mentioned in my introductory spiel, this is a principle of it's not just numbers being thrown at the user. There is a specific reference guide beside the number to show to give context as to where it comes from. So the next is a scenario comparison tab. So the baseline is on the left. This is saved data and it's frozen. It can't be changed. This is alternative data on the right, and this can be edited. So there are 3 override controls. There's tillage, there's nitrogen reduction, and then there's herd multiplier. So if I change one of these to, let's say, reduce tillage, and then you can see the so if I change this and then I put some number here, you can see the changes here, and this is kind of explaining the changes that are happening here. So this is just a plain language explanation that describes what's changed, and it includes an explicit uncertainty band on the soil carbon component, because soil carbon estimates carry roughly 30% uncertainty, so producers should not overinterpret small differences. So the final tab is report. So there's a few different formats here for the report. There's a full report, there's a one-page summary, which is just a shorter summary like so. There's this carbon program template, and as I switch between them, this preview area shows what the reports will look like. The method footer names IPCC 2019 with Canadian refinements, and the report ID is up here, and that helps the recipient verify provenance. So for my design rationale for this, there are 3 design principles that run through the whole system. So first, numbers don't just appear without a source. I have included references and citations of what the emissions figure mean and where they can be traced back to, and I made sure they can be traced back to a published source. So this addresses the credibility problem that spreadsheet-based tools have. Second of all, the system never blocks user input. So as I had said again, it does show a warning at the bottom about out of range values to signify to the user, hey, this seems like a abnormal high value, so you might want to double check that. But then again, we don't know what specific farm operations and what and the magnitude of the farm operations that are happening on a user's farm. The user knows and the producers know, so it's important to have a system that overrides that. Third, live computational feedback, so the user sees the model respond as they enter data, so this builds intuition for what the numbers mean to the user who may not have much knowledge about the mathematics of tracking emissions on Canadian farms. So where the system would need improvement before a full release or a full deployment is the offline mobile path is not implemented in this prototype. The advisor sharing flow exists only as a sketch, and the report export is currently text only rather than PDF format. So each of these is in scope for a follow-up iteration and is documented in the report. So to wrap up, AgriCarbon Lite is a producer-facing emissions tracker that bridges between research-grade tools and ad hoc spreadsheets. It implements 7 concrete user tasks, and it was developed through task-centered design with low-fidelity prototyping and walkthroughs, and it's implemented in Java and Swing with no external dependencies. So the full source code, written report, and this video together fully form my assignment 3 submission. Thank you for watching.